slides for today's session. Kind of like yesterday, I'm going to be switching tasks between PowerPoint and my actual code. I do want to point out, actually, let's go ahead and go to a web browser really quick. And so if we go to our workshop main page on GitHub and scroll through, if you go on down towards this current session, which is session 7, you'll find that the slides you can download, and you can also click here to get the code. And it's a series of zip files. And basically, you're probably not going to be keeping up in real time as we go through today's session. But if you download these different checkpoints, basically you can hit, download into your main PhysiCell directory, type unzip, and it will move all the files and basically catch you up to where I am at that point in the PowerPoint. Do be aware that it's going to overwrite anything that you have in custom. So don't unzip these if you're in the middle of something important, right? But if you are following along in this talk, that would be one way to kind of catch up and get the code for it, or at least pop it open and look and see what's there. That is there and available. And probably this evening I will post recordings. By the way, recordings of sessions 0 through 6 are now online. So actually, if you look back here on the main page and scroll through, you'll see that most of these now have videos links, like this one here. And it's just going to go to PhysiCell's YouTube channel and have whatever particular talk it was. So here's John's tutorial from yesterday, for example. Hello, John. Okay, so we'll go back now. But that is also available. So let's get going now with functions in PhysiCell and use that to kind of launch full on into the full modeling workflow. The goals of this really is to first, again, to recapitulate and further state that full modeling workflow. Interspersed through the slides, I'm going to at least call out handy C++ tidbits that are going to be helpful for working with PhysiCell and with the agents. We won't go into them in super detail and read every line of those slides, but I just want to point out that they're there, and then you can come back to this as reference material. We're going to give the typical form, syntax, and purpose of the PhysiCell functions, and what functions are easily customizable, as there's actually a data structure within the cell called Cell.functions. And we're going to talk about how, once you make a custom function, how do you assign it to a cell definition so that all the cells with that definition will automatically use the rule that you just created. And then we're going to go through an example. We're going to use, we're going to make a phenotype rule where the cells sample their oxygen, and based upon comparing that with their own parameter values, they're going to change their cell birth and death rates. And then motile cells will change the behavior of their motility based upon the oxygen and the environment. Then we have 2 stretch goals, which I'm not sure if we'll get there on the time. But the goal here is to, if we can, I'm going to give you an alternative way, the C++ version of how to control where you place your cells, and C++ functions that can customize the way you color your cells. So those are the stretch goals. But if we don't make them in this oral session, the materials will all be available in the slides that you download. So the full modeling workflow, like the intermediate workflow, right? The very first thing you do whenever you're modeling this is plan, right? You don't touch code. You write down everything that you need to have, right? What's in your microenvironment? What are the diffusing signals that you need to worry about? What kind of cell types do you have? What are the typical parameters? And then, start writing down your hypotheses of the rules. How does birth vary with your signal? How does death vary with your signal? Do they change their secretion in some way? And often in the course of planning that out, you're going to know what the custom variables are that you're going to need to kind of be the parameters of those custom models. And then once you really know what you're doing, then populate the template project, go into the graphical builder, just like you did before, and set up the domain, the microenvironment, your cell definitions. And now we'll also be adding the custom variables and parameters that we planned out. And then when you're done with the graphical side, then we're going to go into C++. You're going to declare your custom functions in custom.h, and you are going to implement them in custom.cpp, and then assign them to your cell definitions, edit your initial placement if you need to, build, run, view results. So a few extra steps, but already you've done a lot of this. So let's kind of continue through that here. Just want to remind you too about the project structure, that most of your custom work will be in a directory called custom modules, and then 2 files, custom.h and custom.cpp, are the ones that we put there in the template project. You're going to have any of your user-defined functions in here. Any globals that you might need for your models could go there. in the custom.cpp, and then you're going to assign, really do edits on your cell types and create cell types is the name of the function. So you can see that's declared here at the top. And then set up tissue is where you're going to modify cell placement as you need to. And see, and then in the main.cpp, you're less likely to modify this. But I want to point out, kind of at the very top of that file, you'll see that that setup microenvironment function is called. So this is going to set up all the diffusing substrates based upon your XML. And then the two functions that we are worrying about, right, create cell types and set up tissue, those are called pretty early in the main loop of the main code. And then later on, you can see that there's a line that's called cell coloring functions, like function pointer. And if you write your own coloring function, this is where you would put it, so that PhysiCell knows how to color the cells with your function instead of something that we made. And then main.cpp, if you look into the main loop, I have a nice little comment line that says custom add-ons could go here. Basically, in the main loop, we update the microenvironment, and then that's this over here. And then we update PhysiCell and run all the stuff automatically. And then if you want to put in some plugin that runs once every delta t, that's where you could put it. Or internally to your function, you could make your own kind of timer that says, when's the next time I need to run this? And you can kind of check against that. But your own plugins could go here in the main loop if you're writing something. So kind of a summary of where things go. We're going to put custom functions to be declared in custom.h. We'll implement them in custom.cpp. We will assign the custom functions to cell definitions and create cell types, because that's kind of where we're modifying the cell types. We're going to declare any custom parameters that you need in custom data and in user parameters in the XML configuration file. And fortunately, we get to use the full graphical editor to do that. So kind of a brief aside, I'm going to tell you some of the things that are available for you so you don't have to code them yourself. And in fact, it's probably better that we unify in this rather than have like a bunch of different random number generators out there. We have made easy interfaces to the Mersenne, the 64-bit Mersenne twister that's been standard in C++ since C++ 11. So uniform random will give you a uniformly distributed number between 0 and 1. Normal random will go from the normal distribution with the mean and standard deviation as specified. We have a couple other nice, cute ones that say if you want a random point on the unit circle, that will give you this. Or if you run a random point on the unit sphere, you can use uniform on unit sphere, because this actually has a kind of a non-intuitive distribution. We have one more that almost no one ever uses, but I think it's handy, is if you have to choose between, let's say, 6 different random events, 0 through 5, if you have a vector of those 6 probabilities, and they better add up to 1, this choose event function will basically choose one of those events with the probabilities that you gave and return an integer saying, that's the thing. It's basically like rolling a dice. So that can be handy for some of your functions. We do have functions for dealing with vectors like normalize. So you can either pass the pointer to your vector, or you can just pass the vector by reference, either way. You can also just return the norm squared, which at least eliminates a square root operation, or you can return the L2 norm, or get the maximum absolute value of your vector. So that sometimes can be handy for your algorithms. We have a couple others that like take CSV character string and turn it into a vector, which can be handy if you want to store a vector of parameters in a string in your configuration file. And of course, all the standard things we overloaded for addition, subtraction, things like that. There are also a couple of functions just for forcing a cell to go into birth or death. Usually, you're not going to want to call these. Usually, you want to just set the birth and the death rates. But sometimes you might want to trigger death in a more specific way, and this can be handy. And then the cell class has a few member data, like there's a flag for is out of domain, which I think, frankly, we need to take a look at in the code and make sure it's working well, but that's something you do. One that might be more useful for the people who are interested in rigid structures is you can actually have agents be unmovable. So they can exert forces on other cells, but the cells can't exert forces on them. They just stay parked. So if you want to make like some kind of a rigid structure or obstacle out of a bunch of little tiny cell agents, that's one possibility, is to go into their initialization and set their flag from is movable to false. So let's get into C++ PhysiCell functions. They almost all have the same standard syntax and form. We wanted to really unify that across PhysiCell as much as we can so that you don't have to think so much about the declaration. But they all have the form of some name, pass the cell's memory address or pointer as the first argument, the phenotype by reference to the second argument, and then delta dt, of like how far in time to advance that particular model. You won't always need it. Now, of course, we could have just passed the pointer by itself, but we found it's a lot easier to deal with syntactically if you also just get direct access to the phenotype as part of the function call. And then once you're within a function, you have the pointer, you have the phenotype, so you can access the cell state via PCell pointing to state. You can access the custom data by PCell custom data, and that was in Anika's overnight talk. You can access the functions we're about to talk about in a second by Cell.functions. Phenotype you've got direct access to, and you can also sample the environment by PCell nearest density vector or PCell nearest gradient vector, which is a vector of gradients in your environment. So there is a data structure called PCell.functions, and that will have function pointers to a variety of functions used by your cell agents. And we'll go through these in a moment, but basically this is where you access and control what is attached to a cell and what rules it has. And you can update those at any time in a simulation. So you can dynamically change the rules in the cell agent if you want to. So a little bit about the purposes of these functions. Volume update function is where we have kind of like the series of ODEs you probably saw in Anika's and Furkan's talks yesterday, that kind of have a basic set of ODEs saying we have a target volume, we have a current volume, and it's going to try to converge towards those target volumes. Usually you can stick with this default function that's good enough, and you just focus on setting the target values in your cell phenotype functions if you need to at all. Update migration bias is saying that when you're in the bias random walk, if the cell is not doing Brownian motion, it needs to have a bias direction. And whenever a cell chooses a new direction, it calls this function update migration bias. So here is where you can set that migration bias. Now, if you use the XML file to set up chemotaxis, basically that's using a pre-cooked chemotaxis migration bias function. But if you want to write your own, this is where you would set it. Custom cell rule is pretty much anything you want it to be, and it is evaluated once per mechanics time step. Update phenotype is also pretty much anything you want it to be, but it's only updated every phenotype time step, so every about 6 minutes by default. Update velocity is where we have our potential functions implemented for cell-cell mechanical interactions. You'll usually just stick with those and just set the parameter values, but of course, if you would like to do upgraded mechanics, something viscoelastic, for example, that would be your place to update it. Note that update velocity in PhysiCell will more or less call update velocity, whatever is there. Then it's going to call the custom cell rule. I'm not sure what order on those, by the way, but basically at the same time, it's going to call those. So at the same sequence, probably the velocity, and then do the custom rule on top of that. And we'll also call the contact functions later. Set orientation is basically to kind of help the cell know what's my unit vector from my base to my apex. If you have a polarized cell with polarized orientation, we really have not developed that very much. But what we do is that when the cell divides, you have that up orientation of the cell from base to apex, and then you have a plane. And so we choose a division plane that passes through that vector, in some random orientation, and that's the division plane. So in particular, that's really important for 2D, right? Because if you had a random orientation vector, you'd have your daughter cells going up out of your XY plane, which is no good. And so for 2D simulations, we actually set orientation to 0, 0, 1 to force cell division to keep in the plane. But that's something that you could write yourself. And then contact functions are more specific about how two cells might be in contact and maybe say have a spring adhesion or something, or pass cell flux. We'll talk more about that tomorrow in session 10. Let me give you a very short example to kind of show you what these things look like. Suppose that you made a phenotype function called myPhenotypeFunction. Well, you would declare it in your custom header file. So be void myPhenotypeFunction with the syntax. And then in custom CPP, you would implement that function. You go void myPhenotypeFunction with the stuff, and then do something with it. So here I just did a really, really simple phenotype function that will say, I'm going to go query a rate parameter from my custom data, and then I'm going to assign it to my death rate, and then return. And that's all I did in this function. And then you need to tell the cell to use this function. So up in that create cell types function, I said, well, let's have the cell default definition .functions.update phenotype use this phenotype function. And that's pretty much it. So now we're going to start getting into a little bit more detailed example of how to actually make this work. Let me take a quick pause. And are there any questions? I think, John, are you moderating again this morning? Okay, I don't see anything in the chat window, so I think I'm going to go ahead and keep pressing forward. And I will call out, at the next opportunity when it might be a good time for questions. I want to take another quick detour in C++ helpers. There are easy ways to access the microenvironment. And so this will be of interest because a lot of the time we want to make our cell functions vary with the microenvironment. So these are cell methods. So it'd be cell.something, right? So one method is just get current voxel index. Oops, there should be an underscore here. Oh yeah, I'm right in here in PowerPoint. I can do that myself. And that gives you the index. So the microenvironment has a mesh data structure, which has a vector of voxels as a linear array. And this will give you an index saying where in my microenvironment am I, which voxel. I'm 47, 248, 3 million. This will tell you where you are in the microenvironment if you want to access it directly. Sometimes that's useful. There's another thing called nearest density vector. I apologize, as a mathematician, to me, density and concentration are the same thing. It's stuff per volume. So I do not distinguish between them like I probably should. But this will give you a vector saying that in my current voxel, in the microenvironment, I'm going to give you a vector of all the diffusing substrates at my position. And so then you can access, oxygen, glucose, or whatever might be in that voxel. Likewise, nearest gradient will say that if you pass this index here, so let's suppose that you found out that oxygen is stored in the second index. So you can do cell.nearest gradient of 3 or 2, and that will give you the gradient of that particular substrate in your particular voxel. So you don't have to go and do your own gradients, and PhysiCell will automatically track all of those and compute them. Or if you want a vector of all the gradients at your position, you do nearest gradient vector, cell.this, and that will give you a vector of vectors, where each component of that vector is that particular gradient. Other key functions, there's a way to search for my current cell, for a cell definition, either by the name of the cell type or by its index, by its ID there in that XML file. Usually you'll just use the character string, and that will return a pointer to the cell definition. You can also find the name of a density or a concentration in the microenvironment. So you say, I can't remember where I stored oxygen, and maybe it's 0, maybe it's 1. You can say, microenvironment dot find density index, type in oxygen as a character string, and it'll find it. This is a really good idea because suppose you're working on a team, and maybe you've memorized that when you wrote it, oxygen is in position 0 and glucose is in position 1. Well, there's nothing to say that sometime down the road, someone else will take your code and add another substrate, and now the indices are not correct. So you don't want to hard code indices when you access the microenvironment. You want to search for it and make sure you find the correct substrate. This will help you prevent surprises in your functions over time. So let's get into the full modeling workflow. And so for my scenario here, I want to kind of keep the scenario somewhat simple, but really show the key concepts here. We're going to have 2 cell populations in this example. Normal tumor cells, or just tumor cells, are going to have entry into the cell cycle is going to be proportional to local oxygen up to some kind of a threshold. So there'd be like a maximum proliferation rate and a minimum cycle entry rate. And that if the oxygen drops below a threshold, we're going to start increasing the probability of necrotic cell death. And then motile tumor cells are going to be nearly the same as the normal tumor cells, but a few modifications. We're going to give them a slower cycling rate, a slower apoptosis rate, but we're going to turn on oxygen chemotaxis. And I'm going to show you a more advanced chemotaxis model in this, just to kind of show you that there are different ways you might want to do that. In fact, for this one, I'm going to have that the cells for low oxygen, we're going to have them wandering very, very randomly, and that as the signal gets stronger, they're going to move more deterministically. So we're going to vary the bias of migration with oxygen level using a Hill function, actually. And then we are also going to say that as you get higher oxygen, the cells start to slow down because they're happier and happier. And so that's kind of our scenario. So first step in our model workflow is to plan. Let's plan. I'm going to give this a very small microenvironment similar to the heterogeneity example from yesterday, -400, 400 by -400, 400 for 2160 minutes of time, which is like a day and a half. We're going to go ahead and use oxygen with the default, most of the default parameters, although I think the decay rate in the default code is wrong. So I want to change that. We're going to set Dirichlet conditions to 38 millimeters of oxygen. So that's 5%. It's like normal physiologic tissue level. And initial condition will be the same. And we're going to turn on the virtual wall so that cells don't accidentally migrate out of the simulation domain. Then we're going to add a handful of custom cell data, which I know in advance just because I've already written out my functions. Usually, this is like the last thing you're going to know. And so what I suggest even is, as you start writing your functions, keep a running total of all the parameters that you need, and then those will be your cell data, your custom cell data. And then we're going to have two cell definitions, tumor cells and motile tumor cells. So let's talk a little bit about the mathematics of our tumor cells. They're going to sample the oxygenation in the tissue. And I'm going to just use a linear ramping here that says that oxygen minus threshold over saturated oxygen over threshold is like a scaling factor, a multiplier, multiplied by my base cycle entry rate. Now I'm going to just use the life cycle model. So there's only one phase in this model. It's from phase 0 to phase 0. So it's R00 here. And so let's kind of look at this behavior. Our saturation is going to be a higher value. We say that above that value, proliferation is saturated. I can't proliferate any faster. Oxygen is no longer the limiting factor. So we want this thing to be 1 at the saturation value. And we want it to be 0, saying at the threshold value where you kind of reach that lowest level, cells no longer enter the cycle. And so I'm just going to go from 5 to 38 millimeters partial pressure. R00 is kind of one of the default values from PhysiCell. And that should be that. And I'm just going to cap this thing. So if this thing exceeds 1, I'll cap it at 1. If it goes below 0, I'll cap it at 0. So it's a linear ramping from those values. And then the tumor cell necrosis also is going to be based on oxygen, saying that above this threshold value, there's no necrosis. Below this thing, as oxygen gets lower and lower and lower, we're going to increase the probability of necrosis until you get down to sigma, oxygen saturation value, saying that's where the necrotic effect saturates or reaches its maximum. So below some value, that's as bad as it gets, and you kind of reach that maximum necrosis rate. So here I'm using a parameter of 0.0028. This is basically saying that cells can survive, I think, like 6 hours on the mean in really, really low oxygen conditions in this particular model. A little bit more planning. Let's talk about tumor cell motility. And so we're going to use something a little bit fancier than the built-in chemotaxis. We're going to use a Hill function. So, oxygen over a half max to Hill power is kind of like our main factor here. And so first for the migration bias, I'm going to just say that it goes up the chemical gradient, and it's supposed to be a normal vector. So it's grad oxygen over normal grad oxygen. In the olden days, you would want to write like plus epsilon down here in case the gradient is 0, but now we have the convention in our code that if a norm is very close to 0, we just spit out 0, 0, 0 as our vector. The speed, we're going to have the speed slow down as the Hill function goes towards 1. So we just do 1 minus this Hill function over here. And the bias will increase as the oxygen goes up. So we'll just have bias go from 0 to 1 as this Hill function approaches 1. And here are my different values here. My speed scale will be 1 micron a minute. The half max will just say 4 millimeters of partial pressure, so fairly low oxygen. Or just 2, so we just to show you something nonlinear. Persistence time will leave us as 15 minutes. So let's go ahead now and take that and actually start our modeling. So the first step in building a project like this is exactly the same as when you're starting with the intermediate workflow. We're going to type make. So if you might have been using some other project before, if that's the case, you would type make reset to go back to a clean slate. Sometimes it's an easy step to miss, right? You type make list projects and it says make file rule not found or something. That means you already have a project populated in. You need to depopulate it and go back to a blank slate before you can type it again. So I did make reset just to make sure. And I'm going to type make template to bring in the template project. I'm going to type make once more just to kind of compile everything that's there. And And so while that's going, actually, I'm going to open a second command window, which I've sneakily have already done. And what I like to do is I like to open this from my PhysiCell directory, and I'm just going to directly execute the model builder from here. And I'm going to execute it. Actually, I'm going to go into the configuration directory and execute from here. That way, my model.xml will write right here in this XML directory, this config directory. So I don't have to do any file copies. It will be where it belongs. So Python ... So this will vary based on where you store things. See here, it was a GUI for XML. Oops, I always mess it up. No, it's GUI. Oh, yeah, it needs to be in bin. There we go. So now I'm calling up the model builder, and it is ready to go. So now we're going to start building our model. I'm going to shrink the screen down just a little bit. Oops, now I can see my other browsing. If anyone wants to help me troubleshoot balancing my declination on my equatorial mount, you're welcome to help. Otherwise, builder. So let's see here. So I'm going to go into the config basics tab first and change the domain to be a little bit smaller just so our simulations are faster. -400, 400, -400, 400. I'm going to leave this alone. Now, if you were doing a 3D simulation, you would modify the Z bounds as well. Okay, we want to turn on the virtual walls so that cells don't leave the domain. I'm going to change the maximum simulation time to 2160 minutes. And let's not save, let's see the threads. Well, on my computer, I have 4 cores with hyperthreading, so I might as well use all 8 of my threads here. And I'm going to change the SVGs. I want them to output a little bit more often because we want to see all that motility. So I'm going to change my SVG outputs to every 15 minutes, once basically per direction change on average. And I'm going to save my data every 360 minutes. And I'm going to go ahead and quit Slack so that that sound goes away. Let's see here. So we've got that. I think we have everything on the basic configuration now. So we set up our domain and how long to save and things like that. Next, we're going to go and start setting up the microenvironment. So I'm going to rename substrate to oxygen. So I'm going to just double click this here. Rename it as oxygen. We're going to leave the diffusion coefficient alone. To change the decay rate to 0.1. That will give me a diffusion length scale of 1,000 microns, or a millimeter in this tissue. Let's see. Let's set the initial condition to 38. This is important not to overlook because we don't want all the cells to die immediately. Let's set the Dirichlet condition also to 38. And I think this is everything. Now, if you want to do fancy boundary conditions, this is where you could do it. Like if you want to have 38 on the top and no flux on the sides and say 5 on the bottom, like some kind of a chemotaxis chamber, that's something you could do here very easily with the Xmin and Xmax bounds. So maybe we'll do another example like that later. But now we've got the microenvironment all set up. Let's start on the cell definition. So we click on cell types. And now I'm going to double click this default and I'm going to rename it to tumor. Hit enter to kind of save it. And I'm going to start editing the phenotype of the tumor. So I'm going to go here on the cycle tab. And I'm going to change the cell cycle model. I'm going to go to the simpler live cell model for now. And I want to use the transition rate representation. So I'll click this little tab button here. And let's set the phase transition from phase 0 to phase 0, which is basically just the division rate here, as 0.00072. That would be in units of minutes inverse. Okay, and then depth, we're going to leave alone. Volume, we'll leave alone. Mechanics, we'll leave that alone. Motility, leave alone. Make sure that these cells are not motile, so leave that unchecked. And go to secretion tab, and there's only one substrate to worry about. There's oxygen, and I just want to make sure that the tumor cells are uptaking oxygen at 10. To take the diffusion coefficient by 10 and square root it, that gives you a diffusion length scale. And so in regions that are packed full of tumor cells, the diffusion length scale ought to be 100 microns with these parameters. And I think that's it. Yeah, and then that's it actually for cell, for tumor. So now we're going to make the motile tumor. So we're going to click on tumor and copy it. So we'll copy all those parameters we just set, and we're going to rename these to motile tumor, and that is that. And now we're going to go modify the motile tumor parameters. So we're going to go into cycle. Remember, we wanted the birth and death rates to be a factor of 10 slower. So one more 0 over there. Go into death. I'm going to change the apoptosis rate to be a factor of 10 slower. So make it 10 to the -6 instead of -5 power. And now we're going to go modify motility. I want to give them a reference speed of 1, persistence time of 15 minutes. Let's just set migration bias to 0 to make it Brownian motion by default, and then we'll worry about the migration bias on our own. But the important thing here is we need to turn motility in these cells. Otherwise, no matter what you do, they're not going to move. So check that to enable, and we've got motility turned on those cells. Secretion should still be, at 10. I'm sorry, actually uptake, right? And then that's that. Now we're going to do something you probably did not do with John's workflow yesterday. We're going to set the custom cell data. So we're going to go here to the Cell Custom Data tab, and I'm going to, either add a new one. You can basically leave sample. It's not going to hurt you to leave that there. But I'm going to start adding these other custom parameters that we need. And by writing it in the custom tab, it will make sure that all the cell types have access to the same custom data. And that's really important for when we write data. So I'm going to click here on make the first value called proliferation saturation. And I should have written down what the values are going to be, but I remember that one's supposed to be 38. Now, I think these are not yet written to the XML file, so I'm not going to bother to fill all these fields out right now, but you probably for good practice should. I guess click the checkbox to make sure it copies over. The next parameter is proliferation threshold. In the new field, check this to make sure that we're grabbing it. The default value ought to be 5. Next parameter is necrosis threshold. That's where necrosis first starts happening. And necrosis starts happening at 5 millimeters partial pressure, at least in our model today. The necrosis effect saturates and reaches its, sorry, PowerPoint got in my way. That is going to max out at 2.5 millimeters partial pressure. And just make sure I didn't have the space. Okay, we're good. Max necrosis rate is our next custom parameter. I'm just going to copy paste this. And I believe that was 0.0028. Oh, I can just barely read it on my screen here. Yeah, 0.0028. Let's check the box here. O2 half max. That's for that hill function. I'm going to set that at 4. And then one last custom parameter called PO2 hill power. And I think we set that at 2. So now we've added all of our custom parameters that will be used in our cell functions. We click here on cell types and click on custom data, and notice that all these have been populated in now. And you could, now if you want these cell types to have different values, this is now a good opportunity to set different values for the different cell types. But here we don't really need to do that. Let's save this. So I'm going to click File and save my model.xml. And now actually, because we ran this from inside the config directory, it should already be where it belongs. Now, if you want to catch up on the code, this would be a perfect point. Session 7 checkpoint 1 will match where we are right now in this code. And so this also seems like a good time to, oh, Randy says I don't have to check the checkboxes. Yay, that's great news. Okay, I'm a little confused on those, so thank you, Randy. But yeah, if you want to catch up, session 7 checkpoint 1, if you unzip that in the root directory of PhysiCell, we'll put the custom files where it needs to be, the config file where it needs to be, and you'll be exactly where we are right now at this point in the lecture. So let's continue now. So we've set up, we've finished the basic, the intermediate model workflow. Now we're going to go and do the C++ bits. And so we're going to go into custom modules. So here I'm just, again, I'm a little bit old school, so I'm just going to use a text editor. Some people are fancier and use real development tools. That's not me. I'm going to go here into custom modules. And I'm just going to open up these two files, custom.h and custom.cpp. And I'm going to slide them over to the right-hand side here of my text editor, just so I know where they are. So let's go into custom.h first. And I'm just going to keep these two open side by side. And hope this font isn't too small for you guys here. But I have three functions to declare. I'm going to make a tumor phenotype, motile tumor phenotype, and motility rule. This will give me an opportunity to set separate motility for the two cell types if I want to later. Notice that they all have the same syntax: the cell pointer, phenotype by reference, and double DT. And so I'm just going to copy these three lines and go into my custom.h file and go to the very bottom and just add my custom variables here. This is the wrong directory. Yeah, I'm like, this is not the right place. You know what? I'm in one of my own projects. That's not good. I need to be over. I thought that looked a little funny. This is where I need to be. Okay, well, that was close. I nearly ruined another project. So yeah, see that there's a whole lot less in custom.h. So let's paste these three function declarations into the bottom here. Common error I make all the time is just to forget the darn semicolon and then wonder why C is arguing with me when I try to compile it. So that's it. We've declared the functions. Now it's time to implement them. And you know, everyone has kind of their own way of coding. But what I like to do before I actually write out the full function is to kind of outline what I'm going to do and then fill in the pieces. So here's kind of the outline of tumor phenotype. I'm going to find the definition of this cell type. Then I'm going to find the index of where oxygen is saved in my microenvironment. And then I'm also going to find the index of my necrosis death model. I mean, it will almost always be 1, but let's just be safe and query for it. And then once I know where things are, I'm going to sample the oxygen in my particular box, so wherever my cell lives. And then I'm going to set the birth rate. I'm using that mathematics we worked out just a moment ago. So first I'm going to get the base birth rate for my cell definition. Then I'll set the multiplier to 1. That's like my default value. And then I'm going to do this linear interpolation. I'm going to sample the oxygen. And if I'm below my saturation, I'm going to write out this linear interpolation. And then if I go below 0, I'm just going to cap it off at 0. And then I'm going to set the transition rate in my cell type to this number. So hopefully this is familiar from sessions 3 and 4 of where things are stored in phenotype. And then likewise, I'm going to do this linear interpolation of the necrosis rate. And then I'm going to do a little trick saying that if I'm dead, I'm going to just set everything to 0 and exit. And then and that will be that. So looks like we're running a little bit slow. So let me speed up just a wee bit. But I'm going to show you the implementation now. So here is the beginning of tumor phenotype. I'm kind of stepping through, right? I find my cell definition using that function I showed you in the C++ tidbits. I find out where my oxygen is in my environment. So here's its index. Then I find out the index of the death model for necrosis. This is a capital N. It is case sensitive, and I apologize for that. Please be aware of it. In the future, we might make that fix the code to be not case sensitive for the search. And then I sample the oxygen in my environment. So here's my vector of densities, and the one we care about is oxygen. Then I'm going to get my base birth rate from my cell definition, and then start the say the multiplier. Then I will sample I've already sampled my oxygen, and if I'm below my saturated value, then I'm going to do this linear interpolation. And if I'm below, cap it off at 0, and then set my actual birth rate as the base rate times this multiplier. So let's go ahead and just paste that in. And then towards the end here, I'm going to do the exact same thing with necrosis. I'm going to reset my multiplier to 0, saying that, you know, generally speaking, there's no necrosis. If I'm below my necrosis threshold, we're in the regime where we do have necrosis, so I'll do my linear interpolation. And if I'm below that saturated value where, you know, we're like super low oxygen, then I've reached my maximum necrosis rate and I saturate and set my multiplier to 1. And then I will say that my necrosis rate is this max necrosis rate for my parameters times the multiplier. You may ask why I don't query the cell definition for the max necrosis rate. And that's because if the cell definition had a necrosis rate that was non-zero, then by default, cells would be necrotic everywhere. And so we want to set that to be default 0. So that's one of the few places we don't put it in the cell definition. And then just here's the end of the function to say that if I am dead, so phenotype.death.dead is true, then I'm going to set all secretion uptake to 0. And I'm going to say, you know, I don't want to enter this function ever again. I'm just going to set my function pointer to null and get out so you don't have to keep doing it. So that is the end of the custom phenotype function. And then the motile tumor phenotype, we're going to actually, whoops, this is the wrong function here. So I'm going to fix that. Hopefully, I think my code had it right in the checkpoint. I want to double check it. Basically, for now, I'm going to make it so that it does the exact same thing, especially if I can copy paste it. That motile phenotype is just going to be the exact same as the tumor phenotype now. Oh, there we go. Do it twice, compiler's not going to be happy. And let's just talk very briefly about the motility rule. I'm going to do kind of the same thing. I'm going to look for the oxygen gradient. And actually, we already have the oxygen gradient, so we just evaluate that and then normalize it. And then going to do this hill function stuff. We're kind of come up with the hill factor, if you will, and then come up with this hill function, this nonlinear function. Set my speed according to the hill function, set my migration bias according to the hill function, and that is it. I'm going to kind of cut to the chase and quickly do this. Paste it in. Kind of running through the code, right? Find my cell definition for reference. I'm not keeping it static because, you know, maybe some other cell uses this rule, although I think for purposes, we don't have to worry about it here. Where is oxygen stored in my environment? Find that index. Sample the oxygen to get the oxygen value. Sample it again to get the gradient. So here is my, and I'm just going to, rather than sampling, I'm just going to overwrite it directly to the cell migration bias direction, saying we're going up the gradient. So my migration bias direction is the gradient. And then I'm going to normalize that vector. So let's see, we already pasted that in. And then we're going to do the fancy bits here. So we are going to say, you know, that, you know, here's a hill factor, right? You're going to use the built-in, you know, power function. You say, you know, you have oxygen divided by the half max to my hill power. And then here's my hill is just that over 1 plus that. I'm going to set my speed. So phenotype.motility.migration speed is my baseline speed times 1 minus hill. So it slows down the better the oxygen gets. And then the migration bias will get less and less random, more and more deterministic, the better the oxygen signal in this model. And then once we're done, you know, we just do the trick. If I'm dead, I'm not going to be motile, so we won't need this function again. And that is it. That's the motility rule. So next in the workflow, we need to assign the functions. So the place to do that is if you go to the very top and search for setup, or no, actually set up for create cell types. Search for that. Kind of scroll through, and there will be a comment in here that says, this is a good place to set custom functions. We are going to take them at their word and paste in this here. So here's how I'm doing it. I first say, find the cell definition for tumor cells and store it in PCD. And then, so it's a pointer to a cell definition. Its functions, in particular, this update phenotype function will be the tumor phenotype function. And then I'm going to go search for my motile tumor cell definition and set its functions.update phenotype to the motile tumor phenotype. And then I'm also going to say that for the motile tumor cell definition, its update migration bias needs to be my motility rule that we just made a second ago. And that's that. So what I want to do now is just modify the parameters a little bit. So I'm going to go open up this mymodel.xml. You can see how all of our settings are where we expect them to be. We have oxygen, decay, we have the live cell model for tumor type. Go all the way to the bottom to user parameters. And I want to seed a few more cells. So I'm going to seed 200 cells rather than, you know, of each type rather than like 5. And now we're ready. So let's build a project. This way I have 2 command lines open, one for the GUI, one for coding. So I'm going to type make, it's going to recompile, it's going to tell me that I did dumb things. Yeah, that makes sense. So I need to go back into custom.cpp and fix my little bug. I want to evaluate this just at, I accidentally copied in too much here. E and BT. And I will go back a few pages and fix this in my notes. Because we're just going to pass those arguments right straight to it. Okay, that should work now. Yep, we're compiling and building. Windows, you would type project and then the name of your config file. If you're in Linux, that would be or in Mac OS, that'd be a / without the exe. But of course, Windows doesn't like that, so we just do project config my model, and we're off and running. This should take like maybe 2 minutes to run. And so let's kind of wrap up the slides here. To compile it, we're going to run it, and I can give you kind of a sneak peek at the results. Actually, I think rather than making an animated GIF, I suggest making it in a movie. It's actually about as faster than making an animated GIF, so that's kind of hilarious. But what we expect to see here is that the gray cells are proliferating, the red cells are proliferating. The gray ought to be proliferating faster, especially if they're close to oxygen, which is around the outer edges of the wall. The red cells want to flee low oxygen and flee towards that wall. So that's what we should be seeing here in our simulation. So let's take a peek here and see. Nope, actually, I don't think I have. Oh, here we go. So let's go into PhysiCell and go into output, and you should see, oh, this is doing a whole lot of nothing. So that is worrisome. Let's see what initial looks like. Well, initialize just fine. So something happened. Let's try it again. Not sure if I just hit something funny or what. Okay, task manager is definitely running. Okay, I don't know what's going on here. This code worked for me. It should work for you. This code is what indeed generated these results. Let's just go ahead and click through and see what it should look like. And so you should see the cells proliferating. The red cells start kind of fleeing out towards the edge. You're going to see a little bit more proliferation towards the outer edges. I'm going to have to troubleshoot what I did wrong in this code. I'm not sure why it's not running.
Paul, would you mind going back to the code? I thought I saw something. If you wanted to.
Sure.
Look at it.
Yeah, John, where did you want to look?
Right there, that function. Are you? Is it returning itself? Is it?
Oh,
that seems very
would
recursive.
be really super dumb recursive. You are absolutely right, John. You've nailed it. So basically, It's stuck in a horrible recursive loop. That makes sense. Oh, John, you've saved the day. Thank you. Let's fix that in the notes too. That's like a fatal error. Yes, that makes all the difference. Oh, that's a relief. I love it when it's something easy. Yay, now we're getting data. So see, here's like my 7th time, and it's going to generate out. This model should take like a minute and a half to run. We are slightly over time, but I want to give you at least a peek of what else is in this set of notes. So I think we're not going to reach our stretch goals, but we did build, in summary, our custom function, and you get here a little bit more custom C++ tidbits. There is function calls to create a cell. Or, if you don't have an argument, then it's going to make the default cell type, whatever cell definition 0 is. You can say create cell type and then pass, by reference a cell definition. and it will make that type. And then the other thing that's really critical is to set the position of that cell type. Oh, are we on to 12:30? Oh, I'm going way fast. Thank you, John. I seem to have not memorized my own agenda, which is not good. Oh, yay, we can meet our stretch goals. This is fantastic. So actually, since we are way more on pace than I thought we were, let's take a pause. Are there any questions? Thank you, John. This is a bit of a whirlwind, but hopefully all these steps, make sense. And then when you can kind of go back to the video, go back to the slides, and kind of take this at pace, this should all hopefully make sense. And I will update the notes because I had a few bug fixes in my notes, and I'll upload the code snapshot as well, just to make sure that fully takes all the way through. Okay, so more tidbits, right? If you want to really control the initialization of your cells beyond just placing them with a CSV file, you can write your own function to place those cells. And so really the core methods you want to know about is the function called create cell with either no arguments that says create the cell default type or pass a cell definition. And then the other thing is, remember when we said yesterday that you should never directly overwrite the cell position because it will mess up some of the underlying data structures. So there's a safe method called assign position. So you do cell.assign position and pass a vector that will play it in the right place and it will set it consistent with all the data structures. So that's really useful for initialization. And so, for example, if you want to create a default cell, I suggest just make a cell pointer. You should never have an uninitiated pointer, so set it to null. Then I'm going to say PCell is create cell. The nice thing is create cell will return a pointer to the thing it just made, so you can do further edits on it after that. So here I'm going to say I'm going to move this cell to position 000. So I'm going to go PCell-assign position, pass this new vector that I had, and that'll be it. And maybe you want to modify the properties of your cell now that you already made it. So you can maybe say, oh, let's set its motility to false. So PCell phenotype motility is motil false. And then maybe set its damage value to 0. And so if you want a more complex initialization, for example, we do this in the heterogeneity example, where we make a whole bunch of tumor cells, and then we go through them and we set them to their own value of their oncoprotein value. So if you want to really, pick from a distribution, for example, this is the type of place you'd want to do that. Or if I want to create a custom cell type, let's say, I want to do a fibroblast. Okay, well, pointer initialized to null. Find the cell definition for fibroblast. I'm going to create a cell called, stored in PCell. And this thing requires you to pass the cell definition not as a pointer, but as itself. So star PCD. And then once I've done it, I'm going to say, oh, let's put this somewhere on the unit circle of radius 3, centered at 4, -2. So I'm just going to make a vector for position, uniform on unit circle. I'm going to multiply that by 3. So now it's the circle of radius 3. And they're going to add on the position, 4, -2, 0. So kind of all the plus equal stuff that you're used to with vectors can happen here. And I'm going to assign this as my cell's position. Other things is you may want to be able to access a list of all the cell agents. This is very handy for initialization. So let's say you place them all randomly first, but now you want to go through and set some properties. There's this all cells data structure, which is a pointer to a vector of all the agents. It's kind of a mouthful. But at the end of the day, here's the syntax. You just loop over all cells, ticket size, and iterate. And the easiest way I've found to do it is when you're in your loop, make a cell pointer and point it to the ith element of this list. And now this is way, way shorter to write than parentheses star, all cells, star, bracket, blah. And that's like a lot to write in error prone. So I just want to do, PCell and then do something to it. So in this case, I'm just reading out some properties for my cell and going through all the cells in my list. So that can be really handy for custom add-ons if you want to do something and apply them to all the cells or query them for some kind of analysis. So let's go into the full workflow and get, oh, yay, so we're into stretch goals now. So I'm really excited. We got a little bit better, farther than I expected to today. What we want to do is kind of make a version 2 of the model. We're going to leave all the code alone. Oh, by the way, let's make sure it worked, right? Make JPEG, make movie. So first make them the JPEG files, then stitch them together into an MP4 file. So this will take just a moment. But we see we picked this to be a very fast example. It ran in under 2 minutes on my like 6-year-old or 8-year-old desktop. So it should run even faster on a modern machine. Let's see here. Oh yeah, and yeah, we're already done with our MP. We're just about done with our MP4. So I'm just going to view my movie. You can see the red cells are moving. Oddly enough, some of them move in, right? Because they're moving away from the oxygen gradient. Well, there's a cluster of gray cells here, so that actually makes them want to move in the middle for the moment, just from the local gradient. So it's kind of fun to see. And then more proliferation on the outside. This is just long enough to start seeing proliferation events, but not take forever to run. Let's see here. Let's get back to our example. So what we're going to do now is this is an answer to one of the questions we had in the session yesterday, saying, is there some way to tell how many of each cell type there should be and where to place them? And so we're going to modify our cell placement function. So, the workflow, basically it's the same as before. We're going to now edit this initial cell placement. We're going to add some new user parameters. This is why I like to leave the model builder open while I'm working, is I'm going to go and modify the user parameters. I'm going to add, so actually what I'm going to do is get it out of full screen here and put this on the left and go to model builder on the right. And now we're going to go into the new user parameters. So I'm going to go here to the user parameters section. And I'm going to rename number of cells to number of tumor cells. And this is in my way, I can't see it. And I'm going to default this to 750 tumor cells. I'm going to add another parameter called number of motile cells. Put this in the second one. I'm going to click the mystery checkboxes. And here I'm going to change the type of parameter. This should be an integer. And let's say that we have initially 50 motile tumor cells. Now here, to facilitate, understandability, okay, this is dimensionless. This is the initial number of tumor cells. So the description is nice to write out. This is initial number of motile tumor cells. I will get rid of the typos when I see them. And let's see here. Let's do one more parameter called max initial. I'm just going to copy paste it just to make sure I don't mistype it. Called max initial distance. That is a double parameter. Let's default that to 250 microns. And blah, blah, blah. That's so what we're going to do is going to say I'm going to randomly seed 750 tumor cells, 50 normal motile tumor cells, and you're going to all make sure that all of them are within 250 microns of the origin when I start out. And then I will go ahead and just resave this model builder. So I just go here to File, Save My Model. Oh, I'm going to go over back. Oh yeah, I guess that's good. Now if I go into like my code editor and click on my model, notice that it says it's been modified. So yes, let's definitely reload it. You see that these new user parameters popped up here in our XML file, along with these descriptions and everything else that we said. So that's good news. I'm just going to browse through and make sure everything looks right. The domain looks good. Save folder, everything like that is good. Oxygen. Cell cycle models got live. Yeah, it looks pretty good. I think we're in good shape. So now we've modified our configuration file to also include some custom parameters for the setup. So the next thing we want to do, I'm going to modify the boundary conditions a little bit. I want to kind of see actually I want to see a little bit more hypoxia in my example now. So I'm going to go back to microenvironment, and I'm going to make this a little bit more hypoxic and set the initial conditions and the boundary conditions to 15. Let's go ahead and just save it again. Notice that it's been changed. And so I reloaded it, and sure enough, my oxygen now has changed to initial condition of 15 and a boundary condition of 15. So we're going to have a little bit more hypoxia now. So you can continue using Model Builder as an easy way to modify your parameter values, or you can edit it in the XML file. And now we're going to modify a set of tissue. And so let me show you how it works in the template project before we mess with it. So I'm going to find the function called setup tissue. And it's doing some things saying, first I'm trying to query the domain size from the bounding box of the microenvironment. So that's in the data structure there. I'm detecting automatically if it's a 2D simulation. And if so, I'm just going to set my Z min and max to 0 and figure out my X, Y, and Z ranges. This is just helpful for randomly placing cells. The next is actually what's placing my cells. And you should recognize now this syntax from earlier, from the custom C++ tidbits, where I'm going to iterate. I'm going to say for each cell definition I have, I'm going to get a pointer to that cell definition. And then I'm going to place however many cells I told it to of that type. So I'm going to just place, I'm going to pick a uniform position somewhere between X min and X max, Y min, Y max, Z min, max. I'm going to create my cell and then move it to this new position. And that's the default cell placement that's in the template project. And what we're going to do is we're going to comment all of that out, because we're going to write our own. So the next line here, I'm going to make this bigger now, is I'm going to write my own little chunk of code. I'm going to copy paste it, and then I'm going to explain what's going on here. So I'm going to query from my parameter file. Those all get dumped into a data structure called parameters. And this parameters.ints, parameters.doubles, parameters.bools, parameters.strings. And you can query them based upon their type. So here I want the double parameter called max initial distance. And then I'm going to find my tumor cells. And I'm going to do basically exactly what I had here. I'm going to go through, and rather than setting X, Y, and Z randomly, I'm going to pick a random angle, theta, and a random radius, distance from the origin, R, between 0 max distance. Now, if you haven't seen this before, if you just picked R randomly with uniform distribution between 0 and 1, then you would have most of your cells piling up in the origin, right? It's like too dense because you have all these angles converging towards the center of your disk. So you actually end up taking the square root of that to get a uniform distribution on the unit disk, and then you multiply by your max distance. Then I'm going to set the 0, the X and Y components to R cosine theta, R sine theta, create my cell, and put it in the position. And so that will place all the tumor cells within that unit, within that disk of radius max initial distance. Then I'm going to do the same thing with the tumor cells, with the motile tumor cells. I'm going to paste in this section here. It's going to do the exact same thing. Now, I've already declared PCD, so I just need to override it, say, look for the motile tumor cell definition, and then I'm going to place all these cells where they belong. And let's see here, that is actually it. So checkpoint 4 in the code should get you here. And so we've changed custom.cpp, so we need to recompile. So make, and I'm going to clean out the data from my last run. Trying to get some of my zoom controls out of my way here. So I'm just going to resize this a little bit. Oh well. So make data cleanup. And then let's rerun this. So remember, it's project./config mymodel.xml. We'll start running this thing. So let's go and see what we got here. Let's look at the initial picture. And see, we now have placed all of our cells randomly within this disk of radius 250 microns. And it's a uniform distribution. So while they are clumped up a bit, they're not like all clumped up in the center and then kind of going out of 1 over R. And so we can even see, like if you go a little bit in time, they start spreading out a bit. I'm not sure what's going on there. I'm worried if there's a bug, but we'll continue it for now. And that is pretty much that going forward. And now it's just running. It should take a couple minutes and we'll get the full simulation run. But yeah, oh yeah, see, now we see some necrotic cells in the center where the oxygen is low. And the red motile cells are trying to escape and they are succeeding. And the motility slows down as the oxygen goes up. So they start kind of becoming kind of equidistant from the tumor, although they'll keep migrating out. And going forward, click on another time. And here they're even farther out from the center. So we are like 2/3 done with the simulation approximately. This should go out to like 144. So this will, this will take about like 2 minutes to run. So now we've, to kind of recap where we are, we made a tumor cell phenotype that varies with oxygen. We made a motile tumor cell phenotype also varies with oxygen, which is the same one for now. And then we made a special rule for changing the migration bias of the motile tumor cells. And then we did a specialized function where we overrode the random placement of cells to have a little bit more control over that initial placement. And that's where we are right now. And we are getting pretty close to done with our simulation. And here I think we really should take a look and actually watch these migrating cells a little bit. So we have about 20 more simulation frames to go, and we're just about there. Cool, I think we will make it through both stretch goals. Okay, yep, we're done. So let's just do make. Oops. Make JPEG, make movie. Now I interrupted my JPEG rules. I'm a little worried that I did something, but. So hopefully we're making a whole bunch of lovely JPEG files. Okay, so if this happens, I did something weird to it. Huh, and now my operating system is doing something weird to me. Well, I don't know if you're even hearing me on Zoom because I had like something crash here.
I can still hear you, Paul.
Yep.
Okay, that's great. My screen, I don't know what's showing you right now, but I'm going to go to the task manager and figure out what is going on here. And whatever is, I'm going to kill image magic. Okay. And now I should be able to get back to wherever I was. I did something basically because when I am running my makefile rule for make JPEG stores some temporary variables in these underscore files. When I interrupted my makefile rule, it didn't clean up those files, which means that the next time I ran the makefile rule, it got confused. That's what happened there. This time we should be in much better shape. So I should not have killed the makefile rule in the middle of the JPEGs is kind of the lesson there. So now we should see a whole bunch of JPEGs popping up like we expected. Cool, that's good that we're not too bad off. Okay, so, oh yeah, we're already done. We already have our movie. So output, let's just look at our movie and see how the tumor cells are, the red cells are kind of wiggly as they migrate out. And then as they get to upper and upper levels of oxygen, they get much more deterministic. And then we have the necrosis here in the center where the oxygen is lowest and more proliferation towards the outer side. So it looks like things are working pretty well. But we'd like to be able to see more of what's going on. Now, of course, we could load all the data up and look at things in Python, and that is a good idea. Oh, it looks like I actually should have made a longer simulation time. So actually, I'm going to go ahead and go back into my GUI, go to config basics. I'm going to rewrite. I want my max simulation time to be 3,600 minutes. Go file, save, and we'll use that next time. Now, of course, you can load the data in Python and do all manner of visualization, but sometimes you just want it to come out that way out the bat. So I'm going to show you how to make a custom coloring function. So we're at our second stretch goal. We've actually made it. And now I'm just going to color non-motile tumor cells. I'm going to say that, what's my current cycling rate compared to my maximum value? And I'm going to use, the colorblind safe coloring function going from blue to yellow. So blue will be at my minimum value, yellow will be at my maximum value. So that's what we're going to do. Coloring functions in SVG for PhysiCell basically have the syntax of you pass a cell pointer and return a vector of 4 strings. The first string is your cytoplasm fill color. Second one is your outer outline of your cell. Third is your nuclear fill color, and then your nuclear outline. So you can use this. There are also some really fun ones we could look at. We actually have a built-in hematoxin eosin coloring function, which is kind of a fun one to use. So there are lots of different options for this. And so, once you make a function, in H, your header file, you declare it. Your CPP file is where you're actually going to implement it, where you're just going to make sure you have a vector of strings and output to that. And then you would use it. So let's do this. I'm going to kind of just quickly declare this function. Probably better declare it then, huh? So let's see here. So in custom.h, I'm going to make a called custom coloring function because I was not very imaginative when I named this thing. So save that in custom.h. Custom.cpp is where we're going to actually implement it. So let's get that started here. I'm going to copy my code and then I'll explain it. So here I'm starting off by saying, actually, I'm going to start off by calling a different coloring function. I'm going to call the paint by numbers coloring function just as before. And I'm going to say, my output is this. So this will already be outputting a vector of 4 strings. And now I'm going to get the cell definition for tumor cells and just store that in PTC for tumor cell. And I'm going to query and say that if I'm not a living tumor cell, then I'm not going to do anything further to the coloring. I'm just going to return the output that I already have. And I saw a question in the chat window. I'll come back to that in just a moment. And now I'm going to get the rest of the coloring function pasted in. So now we're very much at stretch goal land here, but I'm going to go and get the relative birth rate. So I'm going to just make a little double parameter S, and I'm going to say, for my current cell, PC is my input argument, go to my phenotype, to my cell cycle, to the data of my cycle. Remember, cell cycle is 2 things. It's your data of it's the graph structure of your model. So that's the model. And then the parameters for your model, for your cell cycle model, that'd be the data. So phenotype.cycle.data, transition rate from phase 0 to 0, divided by the corresponding quantity for my cell definition. That will give me my relative birth rate. It'll be something between 0 and 1. And then I'm going to start making my color. So first of all, SVG is going to expect integer values for your color, not like 253.702. So I'm going to take 255 times my scaling value here and round it to an integer. I'm going to just make a little character string, 1024 characters, have plenty of room to work. Use a classic sprintf, and this is going to interpolate between blue and yellow. So if my color here, so let's suppose that my color was 0, this would be 0, 0, 255 minus color would be blue. So this starts off at blue when my color value was 0. And then as you get up towards 255, my blue value goes to 0 and my red and my green go up to 255, and that will give you yellow. And then I'm just going to output this to pretty much all of my colors. And so I've made this custom coloring function. And now I'm going to make sure that the code uses it by using this in main.cpp. So I'm going to go ahead and open, go 1 level up, go find my main.cpp. It's here somewhere. There we are. And I'm going to scroll down. This is kind of still towards the top because it's kind of a setup thing. Save a simulation snapshot. Well, we can't. Okay, so if we are saving a simulation, let's go find that. Oh, here we go. Here's my coloring function. So I'm going to basically paste in my function here and comment out the default one. And that should be that. Let's go back to our slides. And yeah, let's go ahead and just recompile it and run it again. So make then project. Okay, and we're off and running. So let's kind of see what's popping up in the output directory. Notice that initial is pretty uniform because we haven't really run the phenotype function yet. So the cells all have their maximum proliferation rate just briefly at the very beginning. So let's just look at the very, very, very next time. Oops, let's do this so it's not jumping around quite so much. So now, you know, a lot of them have a low cycling rate because we've reinitialized everything. We even have a couple of necrotic cells, which worries me. Let's go a little farther in time. Okay, well, this worries me that something's not actually taking here. We have a lot of necrotic cells in the center. I'm not seeing a lot of yellow here like I saw in my demonstration, so I think we've got something not quite right. So let me show you what it's supposed to look like. So here's my movie that I made from this a little bit ago. So see how it's blue and then starting to decrease towards yellow as you get farther out. And that makes sense because we have this constitutive relation that says that oxygen goes up, which ought to increase as you go outward. The cycling rate goes up. And so they should get more and more yellow as you get out there with kind of proliferation. And we have cells kind of wandering around. And we are in good shape here. So I'm not quite sure what's happening in my code that I just pasted in here. But let's let that run a little bit longer and see what's going on. But you can see that we do have the main idea of how to vary the proliferation rates here. I'm a little bit worried that something's happened to my custom data or something. So I'm going to go through, I just want to scroll through my XML. Here are my custom data, proliferation, saturation, threshold. I mean, all that stuff is looking right. So somehow or other, one of two things could be happening. Either I'm not rendering it correctly, or something's happening in the phenotype and it's not actually getting the right cell cycle rate for these guys. I have a feeling that it's more likely if something's happening in my custom coloring function. So I'm going to just have it for temporary debugging, spit out this information. But I think I'll probably need to debug on my own later. So we have quite a few simulation times now. We have this massive necrosis in the center, and then the other cells are, you know, should be proliferating. Although actually that's interesting, right? Do you see how I have 900 agents at the end? Let's see, that's the last simulation. We had 800 at the beginning, 802. Okay, well, there's definitely proliferation. Now, the question is proliferation by who? Is it the red cells or is it the gray or the blue cells? If the proliferation were low, then that would suggest we have a bug in the tumors and the non-motile tumor cells. So that's something we could look at. But I think this is probably a good time to cut off and move on to the questions. So to kind of recap, we've gone through, we've shown you that these are the basics of how to change the coloring function. It looks like I have some troubleshooting to do, so I will do that in my break. But I'm happy to take a couple questions, but let's not eat too much into the break. And let's take a look also just to remind ourselves where we are on the agenda. Randy, did you want, I'm sorry, John, do we have any questions we should look at right now for the moderated questions here?
Sure. The question that, and Randy and I both addressed this,
Okay.
there was a question, so it's about, is it possible to restart a PhysiCell simulation from mid simulation? And
in principle, you could write a data loader that does that, but in practice, we have not yet done that. So the answer is, we'd love to do that. It's on our wish list. It could be a really great hackathon idea where we could load in the cell positions from the, say, the XML or the CSV, and then query other states to kind of set the state variables. That should be possible. We just haven't written it yet. So that's a good question. Other questions? Okay, well, thank you very much, everyone, for joining us for session 7. We got to our scratch goals, so I'm really pleased about that. Let's go ahead and take a break until 1 o'clock Eastern time, and then we will start up with chemical cell-cell communication right back here in the Zoom lecture hall. So thanks very much, everyone, and I will see you all in a bit. Have a great break.